Our goal is to find a maximum strategy in two-player normal form games. Here we have two players, one is maximizing her expected utility, while the opponent is minimizing it. For the sake of simplicity, we assume that player 1 is the maximizer, while player 2 is the minimizer. By definition, a maximum strategy is the strategy of player 1 that maximizes her expected utility when player 2 is trying to minimize it. In practice, it captures the situation in which the opponent of player 1 plays against player 1. We start with a simple example in which all the players have two actions. Player 1 can choose over action A1 or A2, while player 2 over A3 or A4. In the game, only the utility of player 1 is reported, given that the utility of player 2 is unnecessary. We focus now on the strategy space of player 1. Since we have two actions, we have two variables. More precisely, S1 A1 is the probability that action A1 is played by player 1, while S1 A2 is the probability that action A2 is played by player 1. However, S1 A1 and S1 A2 are constrained, and then the strategy space of player 1 is the segment in red in the picture. Now we are interested in understanding the behavior of player 2, given the strategy chosen by player 1. What we can do is studying what action player 2 will choose given the strategy of player 1. Suppose that player 1 plays A1, then player 2 will play A3, given that this action minimizes the utility of player 1. Suppose that player 1 plays A2, then player 2 will play A4, given that this action minimizes the utility of player 1. However, we are interested in understanding the behavior of player 2 for every mixed strategy of player 1. There is a point in the simplex S1A1 equal to 0.4 in which A3 and A4 give the same expected utility to player 1. This point is obtained by equaling the expected utility of player 1 given by the two actions A3 and A4. Focus on the simplex of player 1. We represent the expected utility of player 1 as the strategy of player 1 changes on the simplex. The behavior of player 2 is given as discussed before. Again, when player 1 plays A1, then player 2 plays A3, and the expected utility of player 1 is 0. When player 1 plays A2, then player 2 plays A4, and the expected utility of player 1 is 0. When player 1 plays A1 with probability 0.4, then player 2 plays A3 or A4 indifferently, and the expected utility of player 1 is 1.2. That is the maximum player 1 can achieve. Here another example. In this case, each player has three actions. Player 1 has A1, A2, A3, while player 2 has A4, A5, and A6. We focus on the strategy space of player 1. In this case, the space is three-dimensional, given that the variables are 3. We have S1, A1, S1, A2, we have S1, A3. However, we know that the strategies are constrained to sum to 1. As a result, the strategy space is the face in blue, that is a triangle. We focus on the behavior of player 2. When player 1 plays A1, player 2 plays A5, minimizing the utility of player 1. When player 1 plays a2, player 2 plays a4 or a6 indifferently. When player 1 plays a3, player 2 plays a5. As before, we are interested in understanding the behavior of player 2 for every mixed strategy of player 1. To do that, we can divide the simplex in areas, and we can associate each area with a label corresponding to the action player 2 will play. The edge in red is the region of strategies of player 1 in which the expected utility given by playing a4 and a5 is the same, and it is smaller than the expected utility given by playing a5. It can be obtained by a set of linear constraints over the expected utility of player 1. The edge in red is the region of strategies of player 1 in which the expected utility given by playing a4 and a5 is the same, and it is smaller than the expected utility given by playing a6. Finally, the edge in red is the region of strategies of player 1, in which the expected utility given by playing a5 and a6 is the same, and it is smaller than the expected utility given by playing a4. Now, we take the simplex of player 1 with its division in areas, and we report the value of the expected utility of player 1 as the strategy of player 1 changes. Consider the vertices. Here, player 1 plays a1, player 2 responds with a5, and the expected utility of player 1 is 0. Here, player 1 plays a2, player 2 responds with a4 or a6, and the expected utility of player 1 is 0. Here, player 1 plays a3, player 2 responds with a5, and the expected utility of player 1 is 0. The maximum of the expected utility of player 1 is 1.31, and it is for a fully mixed strategy. We focus on the computation of the maxmin strategy. Initially, we report the definition of the maxmin problem. First, focus on the objective function. It is the expected utility of player 1, where we have the entries of the utility matrix of player 1, the strategy of player 1, and the strategy of player 2. Focus on the minimization problem. Here, the variables are only the strategies of player 2. This is reasonable, since player 2 minimizes the utility of player 1 after that player 1 has chosen her strategy. The constraints of the minimization problem are just that the strategy of player 2 is well defined. Focus now on the maximization problem. Here the variables are the strategies of player 1, and the constraints are just that the strategies are well defined. Focus on the minimization problem. This problem is linear in the variables that we recall are the strategies of player 2. Consider the minimization problem as a primal linear problem. There is only a constraint that we need to consider when deriving the dual problem. It is that one marked in red. This means that we have only one dual variable. We call it v1. Here we have the dual problem. The derivation is standard. By strong duality, the values of the optimal solutions of both problems are the same. Notice that the dual problem is a maximization problem with only one scalar variable v1. The objective function is just a variable multiplied by 1. While we have a lot of constraints, each one requires that v1 is not larger than the expected utility given by an action of player 2. So, given that we are maximizing v1, we have that in an optimal solution, v1 is equal to the expected utility given by at least one action of player 2. Come back to the maxmin problem. Focus again on the minimization problem. By strong duality, we can substitute the primal minimization problem with the dual minimization problem. Now we have two maximization problems, one on sigma 1 and one on v1. We can put together these two problems as reported here, where the variables are both sigma 1, we recall that it is a vector, and v1, we recall that it is a scalar. Notice that in the optimal solution, v1 contains the expected utility of player 1. It is usually called the safety value, given that in every game player 1 can always obtain at least such a value independently of the strategy of player 2. The resulting problem is a linear program, so we know that can be solved in polynomial time. Here are some interesting results known in the literature. A maxmin strategy always exists. It follows from the fact that the feasible region of the linear program is a non-empty compact set. The maxmin value is unique. The same reason as before. Notice that the optimal solution may be not unique, but the optimal solution share the same value. In a zero-sum game, a pair of maxmin strategies is an equilibrium, since every player is playing the best response to the opponent.